We should all say Windows Mobile. Let's all say it together. Windows Mobile. That's right, because that's, what's that? I actually don't speak for, I don't work for Microsoft. I'm an independent consultant. But to allow me to speak at conferences like this, Microsoft injects a little chip back here. And if I say something bad, they just make it hurt. So I normally try not to, because it does hurt significantly. So we'll see. I'm just going to try to talk a little bit about the fun, exciting parts of the internals of the operating system. These are things that the user never has any idea of. I mean, frankly, the user has no idea of the difference between a Palm OS and Windows CE or Windows Mobile OS. What they know of is the difference in the user interface, in your applications. The problem is, to get your applications to look right, you kind of need to know how the operating system works, because otherwise, your app can break. And breaking an application is just, having an application broken in front of the user is just no fun. So what we're going to do today is kind of dive into the operating system, and we're going to dive pretty deep, pretty fast. And then we're going to kind of crawl out of it. Now, there are a number of issues with Windows CE. Some of you have probably heard parts of this talk before. There are a number of issues with Windows CE that kind of keep reoccurring, that will bite you, things that you have to live in. I was at a talk this morning with some of the Windows Mobile people, not a talk, but a meeting with some of the Windows Mobile group at Microsoft, and some of the feedback they were getting from us consultants was, they keep trying to treat a Pocket PC like a Windows desktop in terms of programmers. And it's true that the Pocket PC or Windows CE API is just like the desktop. It's a subset, but if you know Windows development, you can do Windows CE development. If you know Windows development, you can do Pocket PC development, because it is the same construct. The problem is under the covers, under that veneer of the API. You've got this nice, beautiful API up there, and everybody knows it. But underneath it, it's completely different from the desktop. And so we need to look at that and understand why that's different. Now, here's the obligatory slide. I am actually talking Windows CE, so we'll just stop right there with that. Now, what are we going to talk about? Well, what's new with Windows Mobile 2003 and Windows Mobile 2003 Second Edition? The sequel is going to be Windows Mobile 2003 Second Edition Part 2. I'm sorry, I shouldn't have pre-announced that. I'm sure there'll be a longer name in the future. We've only got so many letters in the alphabet, but the beautiful thing about English is you can reuse the letters in a sentence. So. The marketing people make excellent use of that. So we're going to talk about that, what's new in Windows Mobile 2003. I also want to talk about living in the box, what it's like and why this is a problem, because that's important to you. And then we're going to go back, revisit an issue we had last year. I thought we were done with it. I honestly was ready to pull this part of the talk away and say, DLL loading, not a problem, because we have a new OS and that problem is solved. Our friends at Microsoft have solved our problems. They've listened and solved our problems. But you know what? They solved the problem and then they caused it again. There's another problem that's reared its ugly head. That's our process limit issue. And so we need to talk just a little bit about that. Technically, there's not a lot we can discuss, but we can at least look at that. And then finally, I want to go back and look at the compact framework and see how that fits in. Because as we all know, the compact framework solves all problems. Or does it? Now, some of you have probably seen this. If you're a Windows developer on the desktop, you have seen this slide, because this says that if I'm writing an application on the desktop, I have 2 gigabytes of virtual address space. 2 gigabytes. That's enough for anybody, right? I mean, the PC has infinite resources. When do you run out of RAM on a PC? Come on, you got to answer these questions or I'm going to be up here talking alone, and that's no fun. When you run out of hard drive space. That's right. And you go down to Fry's now, and a 200 gig drive is $70. You have infinite memory on a PC. Right? In Pocket PC land, we don't. Because we don't swap RAM to even a compact flash card. We don't swap RAM out. So when you run out of memory, you run out of memory. So they have infinite resources, we don't. They've got a 2 gigabyte address space. We have 32 meg. Big, little, huge infinite. I don't care. Teeny tiny. I better start thinking about it. Because this is important. You got to know this stuff. Now, there's some people on the desktop that think this isn't enough. And that's why you can get Windows Server Enterprise Edition, and it'll allow you to do 3 gig per app. But some people think that's not enough. So that's why they have Windows 64. We're still stuck with 32 meg. And some of you are thinking, no, we're not, Doug. I've seen the new stuff. We've got more. Not really. Not really. And let me tell you, what Microsoft giveth, Microsoft taketh away. Now, how does Microsoft do this? I mean, why do we have in Windows CE, why do we have only 32 meg? Is this some evil plot by Bill to say, go buy our $100 operating system? Don't buy our $15 operating system. Is that why they do this? Is that why this big reserved thing is there? No, that's not why it's there, really. It's there because of the way the operating system works. The Windows CE operating system has a rather unique way of protecting processes. And the way it does that is through a concept called slots. Now, actually, if you talk to real kernel geeks, these are sections. The memory space, it's a 4 gigabyte address space. It's divided up into sections, 32 meg sections. But we call them slots because we've always called them slots before we could see the source code of the operating system. Now, these 32 meg sections, the first 33 of them are important to us. Slot 0 we'll leave for a second, and then we have a slot for every process that can run in the system. We have 32 slots, so how many processes can run in a Windows CE operating system at any one time? 32, exactly. Hey, that can be a problem. We'll talk about that. And so you've only got 32. Now, when a thread in your process is running, that slot is cloned into slot 0. Why is that? Why do we do something that's silly? Why do we have to copy it down? Well, first, we're not copying it. We're manipulating the page table entries of the processor so that literally the virtual address space in your slot is cloned into slot 0. So a write to address 100 in slot 0 is the same as a writing to address 100 in your slot. It's the exact same thing. So we're really not copying, we're cloning. So what that does is that allows protection. We need to be at slot 0 because Win32 requires an app to be loaded at virtual address 0. Actually, it's loaded, the code is loaded at virtual address 64K, but hey, who's counting? So whenever a thread in your process is running, it's mapped down in slot 0. If a thread in your process isn't running, you're not in slot 0. But does that really matter? Do you care when you're not running that you're not where you need to be? If a tree falls in the forest, hey, this is a philosophical question. If a tree falls in a forest and nobody's around, does it make a sound? Well, if your slot isn't where it needs to be, but nothing's running in your slot, do you care? And the answer is no, you don't, in theory, unless you do some really wacky callback stuff. And if you do really wacky callback stuff, you can make no assumptions about where your memory is. There's some fun, wacky stuff you can do there, but if you do it, you can't make any assumptions because you're not in slot 0. And the compiler compiled the code assuming you were. So this is our application memory map. And we've seen this for years. It's basically a 32 meg application memory map. It's exactly the same things that would be on the desktop, except their high end is 2 gig and our high end is 32 meg. The code starts at the first 64K boundary and is demand paged in. Do you know the loader, when it loads your process, doesn't copy any code into your process? The loader doesn't bring any code in. The loader reads your header, sets up your process space, and then jumps to that first line of code, that entry point. And what's the very first thing that happens in your application? Mr. Exception. We get a page fault. So because you call, the code jumps in there, it gets a page fault, the operating system says, whoop, puts that code right in there. And it executes to the end of that page, runs off the end of the page fault. Puts the next one in. And that way, the code is demand paged in, quick launching, just demand paged in as necessary. Device drivers aren't, by the way. Device drivers are locked into memory, so they're the whole thing, if you're curious. One of the fundamental differences between a driver and a DLL is that a driver is locked into memory. So our code is built from the bottom up. From the top down, DLLs are loaded. So eventually, the twain might meet, and when they do, that's a problem. Because we may have lots of DLLs. And in the Windows Mobile 2000, or excuse me, okay, Pocket PC 2000, Pocket PC 2002, they're based on Windows CE 3. And so they have this 32 meg address space, and because of that, they're limited. Apps, the DLLs load down, and if you've got too many DLLs, well, you're in trouble. Now, for every thread in your app, you've got a stack. That's a 64K chunk that's gone for every thread. You've got a heap, at least one heap, that's the local heap. If you create more heaps, you get more chunks gone. You can actually change the default thread size. How many people have ever changed the stack size of a thread? A couple of you got bright lights here. You can do that. By default, your stack size for a thread is only 62 or 58K, depending on what CPU you're running. For you guys, it would be 58K. Well, gee, that's not enough, Doug. Well, I can set the linker switch, and I'll make my stack have a megabyte of space. Is that a good idea? Oh, it depends. There's a good weasel answer. There was a knock on a product that I didn't hear, so I'm not going to. Oh, okay, so you're saying just a programming technique, you want lots of space on the stack because I like it that way. You know what? Not in Windows CE. Do not do that. Because if you set the default stack size of your main stack to a meg of virtual address space, how much virtual address space do you have left? Well, 31 meg? You got a lot less. And oops, let's just launch that second thread in your process. You know what the second thread uses for its default stack size? Same as the first. So in the linker, you can say default thread size is going to be a meg. But when the second thread launches, it's going to also have a meg. And so I'll launch 3 threads, 4 threads, 5 threads. You're out of memory real quick. You're living in a box, people. You're writing code that has to fit in a really tiny box. And you have to be careful of that. So, max stack size I'll ever set is typically about 256K. And that's enough to run the IE control, which you guys really don't get in Windows Mobile, but you could actually secretly copy down. mshtml.dll, the full Internet Explorer 6. It does work. Now, in Windows, Microsoft felt your pain. Microsoft said, we know that's too small, and we feel for you, the developer. We want to make your life better. And so with Windows CE 4.0, actually, Windows CE .NET 4.0, by the way, the .NET didn't mean a thing, 4.0, especially in 4.0 because it didn't support the compact framework. There's some irony. We put it in the name, but we don't support it in the product. But in 4.0, they said, okay, we're going to solve that problem because we're going to give you 64 meg. We're going to double your size. You can thank us later. Or thank me now. Yeah, I like that. So they doubled the size. But actually, that top 32 meg is not to be used any way you want. You can't just use it. Now, by the way, why is this appropriate? When I say Windows CE .NET 4.0 or 4.2, why is that important to the Windows Mobile audience? Because that's what Windows Mobile 2003 runs on top of. It runs on top of Windows CE .NET 4.2. So when you buy a new box that's got Windows Mobile 2003 on it, whether it be a smartphone or a Pocket PC, you've got 64 meg per app. So that's great. They felt our pain. They fixed our problem. Almost. Let's look at it. That top 32 meg can't be used for anything. It can only be used for one thing, and that's for loading DLLs from the operating system. Well, what good is that, Doug? Well, let me tell you. The DLLs would take about 17 meg of a Pocket PC 2002 device. And that only left an application with about 15 meg of space. So with Windows Mobile 2003, they took that 17 meg and shoved it up into slot 1 and left you with 31 meg of free space. Yay! Let's all applaud. Thank you, Microsoft. That's a good thing. I'm serious. We should be happy. I don't see many smiles out there. This is a good thing. This solves a lot of problems. So they put all these DLLs up there. But by the way, as in all things, software software expands to fill available space. So the first thing they did when they realized, hey, we've got 32 extra meg of space, let's put 32 megs of DLLs in there. And that's what they did. So with Windows Mobile 2003, the Pocket PC, the smartphone, especially when you talk Pocket PC Phone Edition, because that has a lot more stuff in it, they used all of slot 1. That's okay, because you couldn't have used it anyway, so it doesn't really matter. Because it's only for ROM-based DLLs. So unless you can slip something in the ROM, in the XIP regions or in the ROM specially mapped regions, it wouldn't help you. But it's still nice, because it gave you, as an application, 32 meg of free space. And your app still was loaded at 64K boundary up. Now you can start using those 1 meg stacks. There you go. You shouldn't, but you could. A lot more space. Now this is just the text of what I just told you. Now how did they do that? How did they perform this alchemy of memory to double the space? Well, they took the kernel, which always used to sit in slot 1. Do you know the operating system takes up about 5 of your slots, 5 of your process spaces? Thank you, Mr. Microsoft. The slot 1 was always the kernel. It was the first process loaded, and they moved it way up into the kernel address space where you can't really see it or use it or play with it. There's actually, like I said, there are sections every 32 meg, so there's actually a number for that section. I just don't know what number that is. I think it's Charlie 0, Charlie 2. It's actually, the virtual address is Charlie 2. The number for this section is different. So they moved that completely out of the way, and that freed up slot 0, and that's how you get that extra 32 meg. But if you look on the slide here, you'll see something a little different. You see the didn't do it. The ghosting on this one is the difference. They don't clone slot 1 everywhere. They can't, right? Because remember, our slots are only 32 meg in size. So when your app flips out and another thread runs from another process, they can't copy slot 1 because there's no room for it. So slot 1 is constant. It always stays there. It's always mapped virtually identically for every process. So only thing that's swapped in and out is slot 0. So Microsoft gave you 64 meg, but then they said, well, we're going to take 32 of that meg, and it's going to be locked down for DLLs, and oh, by the way, we're going to fill it up anyway. So they cleared out some space, but you don't get that 64 meg. You're still at 32. That's all you've got. Oh, Windows CE.NET 4.2, which you guys have automatically. One of the new things they did was they took resource-only DLLs, DLLs that just have fonts and languages and dialog templates, and they put that in slot 7F, way up there just below the 2 gigabyte boundary. So if you load a DLL and it's a resource-only DLL, that's where it's loaded. Is that good for you to know? Absolutely. First of all, Microsoft takes huge advantage of this. And they've separated out, they've parsed out all of their resource stuff. Now, this is good to do anyway. Why do you want to do it anyway? Localization. We have some international people in this audience. I mean, Americans are, and the stereotype is true. Our country, that's all we ever think about in terms of programming. Hey, what? There's one language on the planet, it's English, right? No, it's not. We have to program to different languages. And so we separate, if you're smart when you're designing your app, you put all of your strings in a resource table, and then you swap out the resources for the different languages. And you do the same thing with dialog boxes, because some languages are longer than others. German is 25% longer than English. They've got lots of extra letters. Got to do something with them. That's humor. I guess it just doesn't translate well. So so that's why you have to relay out your dialog boxes. Now, what's important to you about this is that you, if you weren't doing it before, should do it now. You should take all of your resources, slap them in a DLL, and it's a resource-only DLL. Do not put code there. Don't have a DLL main. You can do it. I'd have to go through actually, there's no wizard really to do it, but it's just, you have not found a way to do a resource-only DLL. Send me an email and I'll get something. I don't have the answer for you right now, and I don't have time to actually explore it, but we will. You can do it. And I'll show you the fact that Microsoft is doing it in just a few minutes. So that's important, is to make resource-only DLLs. And if you load any DLL as a data file, it's actually considered the same thing, so it's actually just thrown up there. So this is important because if you've got lots of strings, which you probably do if you've got a really full-fledged app, and your dialog boxes, they need to be thrown up as a resource-only DLL and thrown up into way up there out of your slot. That will save you space. Those of you from companies out there that make products using Pocket PC should be doing the same thing. So this 32 meg space, is it a lot? No, it's not. We've got lots to do in there. And one of the big issues is the virtual memory of the slot. Now, people always get confused, the difference between virtual memory and physical memory. Well, physical memory is a chip, right? So I can have a I can have a Hewlett-Packard device that has 128 meg of RAM in it. Big He-Man RAM. Raw, I've got a BICE. And, I was hearing this morning, people want more now. I want more. I want 256 meg. I want, okay, fine. You go. Get that extra RAM. You know what? It's not going to help our problem at all. Because physical RAM is treated by the operating system as a bucket full of pages. CPU pages. 4K in size. So we've got this giant bucket. Sure, if I get more RAM, I've got a bigger bucket. But I got to pour that bucket, I'll pour the RAM of that bucket into the virtual space that I have. So I can get a bigger bucket. I'm still left with only 32 meg of space. So it doesn't matter how much physical RAM I have in the system. If I've only got 32 meg of virtual address space, it's all got to go there. So extra RAM doesn't help. So virtual memory is what I'm talking about here. It's what your application is written to. When it addresses a pointer, it's some virtual address between 0 and 32 meg, unless it's pointing to a stack variable, in which case it's pointing to your original slot. If you didn't know that. That's a nice way. If you look at a pointer, you can tell if it's pointing to a heap or a stack variable by its address. If it's less than 32 meg, it's pointing to a heap variable. If it's greater than 32 meg, it's pointing back to your original slot. Now, if I want to allocate virtual memory using the crudest way, I use virtual alloc. And on the desktop, we do the same thing. And you'll use this API. You have to call it twice. You call it the first time to say, reserve a block of virtual address space. And so somewhere in this block, I'm going to reserve a page or a dozen. And then you call it again to say, commit physical RAM. And that's taking the bucket and pouring some of the physical RAM into the virtual address space. So committing the RAM is where I actually get physical RAM to actually read and write. On the desktop, people are lazy, so they say, well, I'll just reserve and commit at the same time. Ha-ha, I'm happy. Saves me. I've got one call now instead of two. That works. Except there's a bit of an issue with that. Let's take this. I can guarantee you, even on a device with 128 meg of RAM, that loop will fail. Let's look at that loop in syntax highlighted code. Now, for some reason with this test, I've actually got if it fails loop. But let's just look right here. Here I'm going to allocate memory, reserve and commit at the same time, 512 times. All I want is a K. So if I've got 512K free, this should work every single time. So let's run it and see what happens. My little device over here running. Let's go Control F5. Go over here. Oh, yes, I know. I don't have SP3, so it's complaining. Okay, there's my app. And this is going to be, oh, I just love it when it does this. I'm sorry, we're going to have to actually do something a little different. This is another change with Windows Mobile 2003. If you run a command bar instead of a menu bar, they just overwrite your command bar. Thank you, Windows Mobile 2003. How do we want to do this? This was one of the demos I didn't check before I came in here. I just love that. So, we may not be able to run that test. Except, of course, I've got this device. Let's see if I've got it on here. Same problem. Nope. Okay, so if I run this test, and you actually saw the test run, what would you see? Well, what you would see is each virtual allocation would be aligned on a 64K boundary. Why is that? So my first allocation would be at, say, A1000. My next allocation would be at A1000, at B1000, then C1000, then D1000, then E1000. Why is that? Because of a limitation of Win32. Win32, when you reserve a region of memory, it's aligned on a 64K boundary. And because of that, if I reserve and commit at the same time, every page is going to be aligned on a 64K boundary. How many 64K boundaries do I have in 32 meg? Who wants to do the hex math? Come on, somebody's a geek out there. I'm a geek up here, I admit it. Huh? I still didn't hear that, but that's... There are 512 64K boundaries. So clearly, when you consider the fact that you've got code and stack and other things in here, you're not going to have 512 64K boundaries free. And in fact, this will fail after about 700 or 470 allocations. So how do you solve this problem? You reserve the region first. Commit the data, the memory second. So if I reserve, I have one large block allocated on a 64K boundary, and running through multiple ones. But then the committed pages are page aligned, not region aligned. Just a simple example of what can bite you. This was one of the first bugs I found, or not bugs, first problems I had with one of my apps in Windows CE in 1996, was this problem. Now what if I want to allocate a huge amount of memory? A large block. Something bigger than my slot will fill. Can I do that? The answer is actually yes, I can. If I do a reserve of a block of memory larger than 2 meg, and then I commit the region later, then the reserve will happen not in my slot, but in the large memory area above the slots. And that's nice, because I can put some, if I want a 5 meg buffer, I don't have to chew up my slot space. What's bad about it? Well, every app has access to the same large memory area. So if they want to, they could stomp on your buffer. It's not unlike the slot, the large memory area is not protected across apps. Some of you are smiling going, ha ha ha, I like that. Because now I can allocate memory, send a pointer to another application, and it can read my buffer. Why, yes, it can. Is that a good thing to do? Is that using programming skills for good or evil? Oh, it depends. Oh, we're all so pragmatic here. The answer is no, it's an evil thing. Bad programmer. But Doug, I need to share a buffer. Yes, you may. How do you do that? Well, you can do it with a memory mapped object. With a memory mapped file, which without a file behind it, is called a memory mapped object. And I can allocate that. I can, from small to big, if I only want 1 page or if I want 5 meg. If I create a memory mapped object, it goes up in that large memory area. Somebody else allocates a memory mapped object with the same name, it will point to the same object. But the difference is, what happens if process A somehow dies? In the old way, process A had just allocated a buffer and process B was reading and writing from it. Process A dies, process B goes to read the buffer, what's going to happen? Mr. Exception. Right? Because the buffer will be freed up when process A dies, process B goes over and reads it, death to process B. But if I use memory mapped objects, process A creates the object, process B creates the same object, they point to the same memory, and the use count is 2, because there's a use count for tracking objects. And when process A dies, the use count is decremented to 1, it's still in memory up there. So process B still has access to that buffer. So don't use this trick for allocating a buffer just using virtual alloc to share. You can use this right here, this large virtual alloc. You can use this for large buffers for yourself, but don't tell them to other people, to other processes. If you want to share a buffer between 2 processes, use memory mapped objects. A lot better. So those are just a few of the issues with living in the box. There's a lot of others, and I kind of touched on one, stack size. Maximum stack size. If I create a thread with and specify its stack size. By the way, that's a new feature of Windows Mobile. Actually, it's of Pocket PC, of Windows CE 4.0 and later. Do you know now you can set the default stack size in the linker so that the main thread pops up and it's got a default stack size of anything from 64K to 1 meg if you wanted to. The problem in Pocket PC 2002 and before is every other thread in your app had the exact same stack size. Bad, bad, bad. But with Windows Mobile 2003, when I call create thread, there is a parameter there that we've always ignored that said stack size. And with Windows Mobile 2003, that parameter's active. It works. So now when you launch a secondary thread, you can specify the stack size of that secondary thread for Windows Mobile 2003 and beyond. You cannot do that in Pocket PC 2002 and before. Everything gets the same stack size. So that's always good to know. Another thing about living in the box. Right. So I thought this problem had gone away. DLL load positioning. How many people know of this issue? Oh, so I'm going to slow down and talk to you. When I load a DLL in Windows CE, where does it get loaded? I told you where it got loaded. It gets loaded from the top of your process space down. If it's an XIP DLL, it'll get loaded in slot 1. Or starting with 4.2, it'll get loaded, even if it's an XIP, if it's a ROM-based DLL, they can still put it in slot 1. So that's great. It gets loaded from the top down. But there are some issues here. Because just because you loaded a DLL from the top down, what if somebody else loads the same DLL? Ever thought of that? So if I load a DLL, it's going to be loaded somewhere from the top down in my process space. Excuse me, is the base what? Can you rebase DLLs in Windows CE? Is that what you're asking? That's the tech. In other words, few people know this, but the linker allows, and you can do this on the desktop too. Normally DLLs are linked with a generic address space, which basically means the loader can decide to position a DLL wherever it wants to in the process space. That's the default. Cool people that read books from Jeff Richter and things like that say, hey, look, I can rebase the DLL and say, linker, you tell the operating system that I want this DLL and I want it right here. wow, that's pretty, I'm powerful now. Except when somebody else wants to load it at exactly the same spot. So we don't really do basing of DLLs too much. Can you do that in Windows CE? The answer is yes. It will look at the base address. So if I load another DLL, but again, you can use that for evil and not good, so be careful. If I load another DLL, it can't overlap the first DLL because then the code couldn't run. So Windows CE, the operating system, is pretty smart. It says, okay, I'll load it below the first one. Now what happens next is what's interesting. Another process comes merrily along. I think I'm going to load a DLL. Why don't I load DLL A? Okay. Look where it goes. Why, there's a coincidence. It's going at exactly the same virtual address as it was loaded in the first process. Is that a coincidence? No. In Windows CE, the same DLL will be loaded at the identical virtual address space for every process that loads the DLL. But Doug, what if that process space, what if that memory space isn't available? The DLL won't load. How about that? How about them apples? If that memory space isn't available, the DLL won't load. So if it's been loaded by one app, it's going to be positioned at a certain spot. You load it in a second app, it's going to be at the exact same virtual address. Now, what if I want to load a second DLL, but my own DLL? Well, you know what? The operating system is rather smart. It says, I'm going to leave a gap in the virtual space of the second process because you, the developer, might later on load in DLL B. And so I'm going to leave a gap for DLL B because it has to be at that proper address. So the operating system is very careful about this. That all works until we load another process. Hi, and I'm going to load DLLA because that's always fun to do, because everybody does that. That's what Doug wants in his talk. But then I'm going to load DLLD, otherwise known as SQL Server. Ow. No, it's only a meg in size. To proportion, that's about an 8 meg DLL. But it's easy to add 8 DLLs of 1 meg in size. And before you think, where do I get a meg DLL? Look at the MFC debug DLL. Look at the Olay debug DLL. Look at some of those other DLLs. And then, of course, maybe your app's got some big honkin' DLL. And so it's loaded in that space. And you know what that does? That pushes the load address. There's actually a pointer in the kernel called next load address for the DLL. That pushes it all the way down so that the next new unique DLL that's not based is going to be loaded below DLLD. Oh, look what just happened. It loaded right on top of the stack. Would it load on top of the stack? There are two answers for this, yes or no. Would it load on top of the stack? That's not an answer here. We're not taking that answer. I told you there were two. No, the answer is no. It will not load because that address is not free, so the DLL load will fail. So when you call load library, it's going to fail. How many people check the handle they get back from load library? It always works. No, it doesn't. It doesn't. So start. Check your load library return addresses. And heaven forbid this application were just loading first time and it implicitly linked a DLL and that DLL wouldn't load. The app wouldn't load. Bam! Think about it here for a second. If the DLLs went in there and tried to load, the process implicitly linked a DLL and there was no DLL space, your app's not going to launch. Eek! That's not a good thing. People don't like it when apps don't launch for some reason. I don't know. What's with that? So this is and this is, this has always been the way it has been in Windows CE. We have lived with this since 1.0. Is it a problem? Well, yes and no. There, perhaps. What was the other answer there? It depends. There we go. Let's see why. But it was exacerbated That's just more text. Who wants to read text? It was exacerbated in, I shouldn't say Merlin, I should say Pocket PC 2002. They used something called multiple execute in place regions. And that was to facilitate updates in the field. And when Windows CE boots up, it asks the HAL, the hardware abstraction layer, how many XIP regions do you have? And the region says, why, here they are. And the system says, okay, let's look at the top one. Oh, there's another one. Oh, there's another one. Now I've got 3 regions. And oh, look, there are no more regions. I've got to set my DLL base load address. How am I going to do that? Well, I'm going to take the address of the highest DLL. I'm going to take the address of the lowest DLL. And I'm going to block out that entire area of the virtual address space so that nothing shall be loaded that isn't XIP. Is that a good thing or a bad thing? It's bad. It's really bad if, say, a large, huge software company decides to implement this, and they put these huge gaps between the XIP regions. Perhaps they would put a 4 meg gap up there. Would they ever do that? I can't imagine anybody being that silly. Why? Yes. They will. Such that when a Pocket PC runs, 2002, the first DLL load address is at about the 15 meg boundary, meaning half of your slot was gone. And in fact, you know, I got rushed up here. Let's see, did we ever find any plugs up here? We never found any plugs, so I'm not going to get to demo that. I'm really disappointed about that. Well, we're going to demo something else, something that's more fun, and yet, I really love this phone, okay? I am not going to criticize the phone for what I'm about to show you, so don't take this as criticism of this phone, because I love this phone. You can win this phone if you fill out your evals. This is a cool phone. I love it. But now let's take a cable here. It's always nice to have cables. Let's unplug you. You weren't a lot of good, were you? Put you in. And to be honest, I don't even need to put this on the Elmo because I'm not going to. There we go. Hello. Oh, look. It says I have to talk. I can dismiss that. Let's go over here and launch a little program I've got. And I want you to look at this app. This is a little app that I wrote. I'm going to connect to a device. This is a smartphone 2002, because I have not upgraded it, which apparently you can do on the floor. I'm really excited about that. Beware, someone says. I love it when this happens. There we go. So what this is going to show you up on the left side there are the processes. Come on, you can show me the processes. It would be really nice. Thank you. These are the various processes for the go away for the process for the system that's running. And if I come over here and I look, let's see, let's just take CE Manager, which is the debug deal, and I go over here, and that's a picture of the 32 megabyte address space. Now remember, this is Windows Mobile 2002. Oh, excuse me, Smartphone 2002. So there's 32 meg there. The red is code. The blue is data. Very small application, lots of buffers at the bottom. What's all this stuff? These are DLLs. And as you pick through the various areas here, you'll see that there are more DLLs. These are the DLLs mapped into the space. Because an app doesn't map every DLL into its space. Now, except one. Actually, the kernel maps every single DLL. And if you look at the kernel here, wow. So that's what on a smartphone. Now, is that the one you need to look at? No, actually, the area here, look, the kernel, again, is the kernel of the operating system. That's NK. FileSys is the part that does the file system, such as the object store. Now, GUI does the graphics and the GUI stuff. There's some interesting heaps there. The device manager is the one that loads all of your device drivers. Now, does anybody see anything wrong with that picture? Do you notice that they have allocated data memory above the lowest DLL? Can you see the blue above the red sliver right here? So literally, they're literally out of space on this device. If I tried to add a device driver and did a delay load on it, it wouldn't happen. So that's one of the reasons to upgrade, even if you have to beware. This is a limitation of the operating system, Smartphone 2002, not of the device itself. So what did they do to fix that? Well, we said we doubled the regions in 2000, in Pocket PC, in the Windows CE 4.0. And I want to just go over and, actually I am going to go back to this device for a second. Let me go over and close my app. And if you look at this device in a minute, which we'll do, I'm just going to go ahead and plug it in so it'll do an active sync. There we go. Let's go back to my slides for a second while that's active syncing. Oops, got to do that again. So that's more text. So on the Pocket PC 2002, you saw that it was using a lot of this. And by the way, this when I say Pocket PC, you can also say smartphone, because it's almost identical. In fact, it's usually a little worse on the smartphone sometimes. So they basically they left you with about 15 meg of space. Now, the smartphone, it was even less, but on a Pocket PC, it was about 15 meg. On a Windows Mobile 2003 device, remember, they doubled your space. That's great. Gift you about 31. Now, I have a device here that I'm not going to put up, and I feel sorry because a friend of mine that brought it here went to his hotel to get it back. This is a T-Mobile. It's running non-second edition. This is standard Windows Mobile 2003. Now, because it's branded by an unnamed vendor out there, a telephony vendor, they've added their own goop inside it. And so this 31 meg actually goes down to about 20 meg. So when I talk about these numbers here, I'm talking about numbers that you get from a straight build from Microsoft, which frankly you guys never see because your stuff is always interpreted by the OEM who adds more goop, adds more programs. Things that customers like. I'm not complaining. It's just that it fills up more space. Now, on an Ozone Update device, oops, sorry, second edition. Sorry about the audio that I just hurt somebody in the back. How much space do you think is left? What Microsoft giveth, Microsoft taketh away. So you're already down to about 18 meg. This is on my device that is not a branded device. It's a device I got flashed up at the lab at Microsoft, so it has no OEM cool stuff added. So you can imagine what you're going to start seeing when you get OEM cool stuff added. And to you OEM cool people out there, be careful what you add. The developer you hurt may be one of your own. Be careful about this. You're already using too much space. And I actually got the scoop of why this happened today at the meeting this morning. And it was because Microsoft adjusted the way they build the image to facilitate updates. They created not 7 or 8 update regions, XIP regions. They've got like 20. And each region actually has some gaps between them for technical and logistical reasons. And that's why they use so much more space. They don't actually have that much more code. They just used that. They just expanded to fill available memory, right? Unfortunately, the memory they expanded into was ours. Anyway, beware. What's that? Solutions he asks for. Workarounds we have. First of all, don't build lots of tiny DLLs that scurry about. Build big DLLs. Why? Because every DLL takes up 64K. If I write a 5K DLL, it takes up 64K of virtual address space. So if I've got 4 DLLs, 5K each, that's going to be 256K of virtual address space used. But if I combine those 4 DLLs into one, I'm going to use 64K, not 256K. So if you're writing an app, don't write lots of little DLLs. Second thing, by the way, you'd be amazed how much that saves of space. That solves many people's problem. Because they come from the desktop, they think they want all these updates, so they write, oodles of little teeny tiny DLLs. Well, that facilitates my wireless download to update that DLL. I don't have to download a big one. I'm sorry. We've got bigger problems to deal with. And the bigger problems are there. This is a huge dominating problem that you're going to have to deal with if you write an app of any significance. Second thing, if you really need to get tight, size your DLLs basically a page or two under 64K. So make them 60K in size, or 25K in size, 125K in size, or maybe 195K in size. In other words, just under the 64K boundary. Because that's what you're trying to conserve, are these 64K boundaries. You can always move code into your application out of your DLLs. Even if you have to do out-of-proc servers or out-of-proc support, sometimes that's what's necessary. If you've got a megabyte of stuff you need in a DLL, perhaps you need to put it over in another process. Now, you're going to have to be really smart in how you do the inter-process communication, or you could kill the performance. But you still might want to put it over into another process. That's going to cause another problem, but that's later on in the slides. Finally, in the worst case situations where I've had to deal with this, I've literally had to go in and write a little application that launches just after the file system loads, that literally does a load library on every DLL I'm worried about, and loads them in a very specific order. So that the last process that needs the big honkin' DLL is the last DLL to load, so that all the other DLLs are way high. Now, but Doug, that's going to use up space. Well, no, actually it's not. Because all I'm doing is calling a load library on it, and it's going to get called load library in the other applications anyway, and these are very specific DLLs. So you can actually order them and fit your space. The other thing to do is be careful about your stack size. Don't do those 1 meg stacks. It doesn't depend. Unless you know exactly what you're doing, it's a very dangerous thing. Any other questions on this stuff? Anybody seen this problem? A few of you have seen these problems. How many people know of this problem? 7 people raise their hand. How many people have seen this problem and have been bitten by it? 7 people. It's sort of like you go up and you ask a person, do you back up your hard drive? And if the answer is yes, you ask them, then the next question is, when did it crash? Nobody backs up until they lose data. And then after that, they become quite religious about it. It's the loss that hits. And in here, it's when your app doesn't work that you learn about this stuff. So don't wait. Plan now. Because otherwise, you'll be doing it late in the field test part of your development. And that's not the time to be doing it. If you've got a DLL just for giggles, I mean, if you just substituted code out and pushed it into a DLL for fun, then yeah, that's not the thing to do. If you put it out there to share among multiple processes, then you can certainly make a balance of how to do it then. But don't create DLLs just for the sake of creating DLLs. They do take up space. So that's the it depends answer. It's, does the DLL serve a functional purpose aside from just holding code for this one process? Other questions? We've got more to talk about, but I just wanted to. You can ask later. You can cogitate. Well, as we all know, the thing that's going to solve everybody's problem in the future is the compact framework. The compact framework is just the perfect solution for all people. Well, isn't it? Haven't you read the marketing? I mean, my neck's not hurting. It will solve all of your problems. And it will make all this ugliness go away. Or will it? Let's refer back to the little program that we had running. And I'm going to do that by going to the desktop and launching the viewer again on this app. And this is actually a different look of the program because I actually updated it. I've been playing with this. And now we're going to a Pocket PC 2000 device. And so we'll bring that up right here. So let's just leave this up and running. And we can see that we've got apps running down here. And by the way, if we look at the device manager now, let's go back up and look at the device manager. We see that we have this high region. This is the area that holds the second. This is slot 1. And the low slot, you still have space. So there's a huge difference here. And this is a phone edition device, right? So in this phone edition device, there's still space between, especially in the device manager, between all of the threads. Those are threads right there. I mean, stacks for all the threads. If you see the dark on the right-hand side, those are stacks. If the dark is on the left-hand side, those are heaps, because they're committed from the top down instead of the bottom up. But you can see we've got a lot of gaps there, so we're cool with that. Now let's go over here and let's launch this application. And this application, some of you may have seen. We will see if it launches over there. And it does. And let's go over into the Elmo. And this is a really ugly application, and all it does is allocate memory. So let's allocate a meg of RAM. Oh, wait, not of RAM, of course. I'm going to allocate on the managed heap. That's not real RAM. And let's go get another 1 meg buffer on the managed heap. And if we go back and we look at our application, let's do a refresh here. And we should see our application down here at the bottom. Let's try this again. There we are. And if we look at our application now, we will see that we've got some buffers down here that have been allocated. Now, those buffers are pretty cheesy-looking buffers. So why don't we go over here? You don't need to see this. I'm going to allocate 4 meg and another 4 meg buffer. And now let's do a refresh. And as it goes off and it goes and checks that out, we're not getting our allocations, are we? Oh, good. I like it when things don't work. Let's do this real quick. See if I can get it to refresh and actually do something what I want it to do. Oh, we're not going to get our memory allocations. It's, I think, in my viewer program, so I'm going to restart it. I love it when a demo comes together. Or maybe truly it's just not allocating that buffer, but I know it is. There we go. Why are we not getting this to work? Well, we're not going to waste time with it if we don't see it. Look at that. We're getting 0. .NET's so efficient it doesn't allocate anything. That's actually absolutely wrong. And the point being that I can't show you, unless I can get the memory viewer to actually work here. See, there's the memory. And if you look at how much memory is allocated, once you look at these, if we sort by by address, you're seeing that we're getting some huge allocations. Those are actually images. Those aren't, you know what? Our application, this is, I'm going to try to shut the application down and try it one more time. And then if that doesn't work, we're done. Let me just try to run this one more time and see if I can get this to work. Because it's kind of fun to watch, and it's important for you to see. Okay, let's do a refresh. Ah, there you are, you little dickens. Okay, so there's our first buffer. Let's allocate a 4 meg buffer and allocate another 4 meg buffer and do a refresh. And you can, there we go. So there's our buffers. Yes, they are allocated. So no, it's not magic. They do go in there and look at our virtual address space. But now if we allocate everything, let's see what the compact framework is going to do for us. And I think it's going to work because I just hit F5. Oh, I love it when it says program memory low and it terminates my app. And now it's trying to terminate ActiveSync. And it doesn't give me an option to just say no, deny the memory. So it actually terminated my app and terminated my I'm going to do this one last time, and we're going to have some fun with it. Because I'm determined. So anyway, while that's starting up, understand that what's going to happen is that the managed heap allocates virtual memory from within your slot. And it's going to do that no matter what you do. It's going to allocate memory within the slot. And I'm just going to connect up and see if I can get this last time to work. And normally when I throw an exception over there and it shuts everything down, oh, ActiveSync is not up because it shut it down. Normally what's going to happen is it will go off and allocate memory everywhere in the virtual address space. Meaning it will allocate memory. Don't you just love it when this happens? You guys have never seen that dialogue, have you? Not a one of you. This is a new dialogue. I should show you this dialogue. This is the I'm taunting you dialogue. Because you know it's not connecting. And yet that's what it says it's doing. So, demo fails. Oh, device notification. Okay, you're so toast I'm not talking to you anymore. Let me just tell you what's going to happen. The system is going to go in there and the managed heap will grab every single part of your virtual address space in your slot. Everything it can see. And it doesn't care if that was a place where you thought a DLL might be loaded. The managed heap will go grab all the whole parts of that bottom 32 meg of that slot. And when it does that, and you go later try to load a DLL that was not in the XIP, but was a DLL that you brought along because for some reason, some of you need to p-invoke. Those of you that know what I'm talking about are managed coders, because if you don't do compact framework, you may not know p-invoke, but if you are a compact framework developer, you know p-invoke. That is the ability to call out of the framework. And you need to do that. So if you call into your own DLL and the system's already allocated all the memory, your DLL is going to fail to load. Now, here's the other thing about the compact framework. When does it load the DLL that you're going to call? It loads it the first time you call the DLL. So if I'm running for 2 or 3 days in my application, in my managed application, and then later I need to do a p-invoke to a DLL that I wrote, those 2 or 3 days, the managed heap may have grown and filled and filled and filled my entire slot, and I try to call the p-invoke, it's going to fail because there's no room for that DLL to load. So how do you solve that problem? Well, anytime you're going to ship your own DLLs with your managed code, you should have kind of a get version, just for maintainability, a get version API that you can call down to make sure that the DLL that's down there is the one you expect. And do that when your form loads. Once you make the call into the DLL, then that DLL will be loaded into your process space before the managed heap grows to become the monster that ate all the memory. So load your DLLs early, your unmanaged DLLs early. Call them early in your code. One last problem I want to talk to you about. This, is interesting because I didn't think this would ever really be a problem. But as we all know, software expands to fill available anything, to consume all resources on any kind of device anywhere. And in this case, there's a device that's out there that ships with about 25 processes running off a cold boot. So, let's do ActiveSync. Well, how many processes does ActiveSync take? It takes 3. Repilog, which is the main process for ActiveSync. RapiServe, which is the Rappi server process. And RNA app, which is the dial-up networking kind of support that's in there. So there's 3 processes that launch because of ActiveSync. Oh, that's up to 28. Well, I think I'll do the calendar today, and then I'll do the address book, and then I'll do, inbox, and then oops, I've run out of space. Worst case, what normally happens is they launch inbox and calendar and address book, and then they try to do an ActiveSync. Oops, then it doesn't quite work so well. Because a lot of your applications are not written to close quietly. You need to learn to close quietly. You need to learn not to pop up a dialog, I'm closing now. You need to just close down quietly. Second of all, don't be writing processes that should be services. But what do you mean by that, Doug? Don't write an app that's going to be sitting in the background churning, like a camera app. Hint, hint. You don't need a camera app. You need a camera service. You need code running in the background to manage the camera that can provide a callable API for other processes that can use when you want to view the pics. That's how you do it. And how do you write a service? Well, it's all in the documentation for Platform Builder and even in Pocket PC. It's in the Windows CE documentation. A service is nothing more than a DLL that actually is loaded by a particular process called, conveniently enough, oh, you're still dead, aren't you? The Services Manager. It's called the Services Manager. So it's a process that's always running on your Windows Mobile 2003 device. By the way, in Pocket PC 2002, you couldn't do this. The Services Manager wasn't brought in until 4.0. But you can still write, if you had to, a device driver that's loaded by the Device Manager. Which, when you think about it, the camera is a device. Maybe it should be a device driver, or maybe it should be a service. It shouldn't be its own standalone app that runs in the background. So don't write apps willy-nilly. Write processes or applications that the user sees. Anything the user doesn't see should be a service. Here's a white paper on writing services. These slides will be on the server. They're not on the server right now for the conference, but they will be on the server as soon as I get over to the speaker room and give them my little USB dongle that has the slides. Never create two processes where one will do. But Doug, 10 minutes ago you told me that to reduce DLLs, put the stuff in another process. I know, I did, didn't I? I didn't say this was easy. I said this was stuff you have to think about. So think about it. Think about what you need to do. Balance your system with your hardware. Sometimes you need more DLLs, sometimes you need more processes. But know what you're doing. And be aware of these issues. The XIP DLLs, if you've got an embedded device, if you can go to, there are companies out there like Symbol and Intermec that actually build devices that have Windows CE, not Windows Mobile. Ow. So one of the Windows Mobile people has the button now. It's still Microsoft. That's good, right? Well, that didn't hurt. So you can get non-Pocket PC stuff, devices, that will run the same software. I know that's a shock to the Windows Mobile people, but you really can. You won't have the home screen or the Today screen, things like that. You won't have all the value add of the Windows Mobile, but you'll have the same operating system, and your app probably will run if it's built on 4.2, an embedded version of 4.2. Write your apps so that they do shut down gracefully, okay, and do it quietly and quickly. There's no reason your app should ever have to prevent itself from closing. If you have an app that you think should always be running, it probably should be a service, not an app, not a process. So if you think that you have to hold off those WM close messages, no, I'm not stopping now. I've got a camera to manage. Well, then maybe I should be a service, not a process. So whenever you start thinking about how to stop your app from terminating, I want you to start writing a service. We've talked about managed memory, and I don't know actually how this slide got mixed up, but it was basically for the compact framework stuff. So, know your system. Know the limits of your system. It's important to understand how the system works. Understand that the DLL load issue, it's back. And you're not seeing too many Windows second edition devices out there, but soon you will, and soon the problem will return. So start thinking about the fact that the problems you used to have with Pocket PC 2002 in terms of DLL loading are now back with Windows with the second edition. Understand the 32 process image limit. There are a couple of good talks that you should go to. If you can learn to write a driver, you know how to write a service. They're almost identical. Go see that. And then excellent memory power and management. I don't know. The title just sounds cool. So I'm sure it'll be a good topic. Because after all, if the title's cool, the talk is too. Right?
Fill out your evals. There is the URL right there for the evals. If you fill out the evals and you are selected, you may win one of these. Motorola. By the way, I checked my evals last night. I had 16 evals from yesterday's very crowded session, which means one of those 16s is going to win a phone unless you all rush out and do an eval on yesterday's session too, which you can do. I just asked. So you can eval yesterday's. Well, don't do it unless you're going to give me a good grade. Or you can eval, and you can eval today. So remember, if you do an eval, you can win a phone. 9 is good, 1 is bad. Thanks.